So we made it to the end of the chapter. So on this part, we will continue doing stoichiometry using mole to mole ratio and so on to do calculations. However, we are going to do it now with energy. So the same way you can relate the amount of reactants to the amount of products, you can relate the amount of reactants or the amount of products to the energy produced or consumed by the reaction. So that's what we're doing here. We're going to calculate the amount of thermal energy, which is going to be reflected by an increase or decrease in temperature, which is either absorbed or produced or emitted by a chemical reaction. This is what we call thermochemical equations. But before we do that, let's understand the vocabulary we use when we're talking about a chemical reaction producing or needing energy. So what we use is exothermic, exo like exit. So energy is leaving the reaction, energy is being produced, and endothermic, which means energy is being absorbed by the reaction. So the best way to see this is with some examples. So let's look at this. Butane gas burning in a lighter. So if I have a lighter on my hand and I click it and I see the flame, do I feel cold or hot? And your answer is, I'm gonna feel the warmth coming out of the reaction, right? So if I'm feeling the warmth coming out of the reaction, this reaction is exothermic because there's heat coming out or exiting the reaction. Another example, the reaction that occurs in the chemical cold packs used to ice athletic injuries. So if I have a cold pack and I activate it, I expect for it to feel cold to me because I want to cool down my athletic injuries. So that means my brain is feeling cold, which means I'm losing energy. If I was gaining energy like from the flame, I will feel hot. If I'm feeling cold, it's because I'm losing energy. And something is taking that energy. What's taking that energy? The reaction happening on the cold pack. So the reaction happening on the cold pack is taking energy away from me. So it's taking energy in. So therefore, the process on the reaction is going to be endothermic. So you can decide if something that is happening is exothermic or endothermic by just thinking about how you feel. If you're feeling heat coming to you, that means the reaction is releasing that heat. If you're feeling cold, it's because your body is losing heat and that heat is going to the reaction, so that would be endothermic. So the burning of a wax candle. If I have a candle and I put it close to my face, I'm gonna feel warm. So that means that the burning of the candle is exothermic. So we're gonna say that when something releases heat, that's gonna be exothermic. When something needs heat, that's gonna be endothermic. So on a chemical reaction, if the heat is part of the product, it's exothermic. If the heat is part of the reactant, it's endothermic. Also, we're gonna measure the heat like you learned on previous chapters using joules probably or kilojoules. And if this happens to be negative, that's the same as saying that it's exothermic. If the heat which we measure in kilojoules happens to be positive, that's the same as endothermic. So keep that in mind. So let's practice that. Let's go ahead and do your daily work. So when we're talking about heat, which is what we call energy, is a form of energy. For in the terms of chemical reaction, we're gonna call that the change in enthalpy. So on the change of enthalpy, we're gonna define it like delta H of the reaction. So every time you see the delta H of the reaction, we're referring to the change in heat, which is the change in energy. So if we have a chemical reaction that includes energy, right, the change in enthalpy of the reaction, we see that this one is negative, so this one is a exothermic reaction. But you already knew that from chapter 3, I believe. What's new now is that this reaction is telling you that for every 1 mole of A, you are going to produce 55 kilojoules. I don't have to say negative because I said produce, which is what the negative means. The same way, for every 2 moles of B, you're going to produce 55 kilojoules. And every time you produce 1 mole of C, you are going to produce also 55 kilojoules. So this is what I'm saying. For every 1 mole of A, you are going to produce 55 kilojoules. For every 2 moles of B, you're going to produce 55 kilojoules. For every 1 mole of C, you're going to produce 55 kilojoules. And you can do it backwards, right? 55 kilojoules are produced for every 1 mole of A, and so on. So those are conversion factors. So you know how to use conversion factors. So let's do some problems with conversion factors. Determine the amount of heat. So we need to find the heat, the enthalpy, given this amount. So how do I do that? Given 1 mole of A, can you tell me how many kilojoules that will be? Using the train track foolproof method, you can say, well, I do not want the moles of A because I'm looking for kilojoules. So I cancel my mole of A and I get my kilojoules. But I need those numbers. Those numbers come from the balance equation. Minus 55 goes with the kilojoules, and 1 goes with the A. So 1 mole of A is definitely going to produce 55 kilojoules. What about B? 2 moles of A. So if I have 2 moles of A, then instead the setup is still the same, but now, since I have double the moles, I should be able to produce double the energy. What about B? If I have 1 mole of B, can you tell me how many kilojoules that should be? Using the balance equation, I know that for every 2 moles of B, I'm going to produce 55 kilojoules. Therefore, minus 55 divided by 2, that's going to be minus 27.5 kilojoules. And what about if I have 2 moles of B? If I have 2 moles of B, then I should be able to produce half of that, double that, sorry. which is going to be minus 55 kilojoules. So nothing new here. There's something new. The new thing is that you can do the same way you can do mole to mole ratio, you can do mole to energy or energy to mole ratio. And then you just use it as a conversion factor. So with that said, you should be able to do this problem. Actually, not yet. So let me show you something else. Sorry for that. So let's do another problem before you go into your daily work. So we know that octane is part of the gasoline, and it burns to give power to the engine by following this balance equation, which is a thermochemical equation because it includes energy, and it's gonna be exothermic. So if you burn octane, you're gonna feel hot. What mass of octane is required to produce this much of energy? So it's asking us the mass of octane if we begin with 1.55 times 10 to the 3 kilojoules. Remember, like I told you before, this is nothing more than conversion factors. I do not want my kilojoules because I want the grams of octane, but I have a balance equation. Balance equation is never given on grams. It's always, always, always moles. So you're gonna have to find the mole first, and then you're gonna get rid of the moles of octane using the molar mass of octane. So these numbers at the beginning, where I have the kilojoule is gonna be minus 5074.1, and the moles of octane are gonna be just 1. And for the molar mass, 1 mole of octane is gonna be 96 plus 18, 114 grams. So that tells me that for me to be able to produce that much energy, 1.55 times 10 to the 3 kilojoules, I'm gonna need to burn how much? Let me find out. So if I have 1.55 times 10 to the third, multiplied by 114 grams, divided by 74.1 kilojoules, that's gonna equal 34.8. Notice that this is negative just because it's telling us that it's exothermic. It wouldn't make any sense to make these negatives because mass cannot be negative. So the negative symbol on energy is not really a mathematical negative symbol. It's just a label telling you exothermic or endothermic if it happens to be positive. So do not put the negative sign there because it doesn't make sense. Mass cannot be negative. And this is what it means. If I burn 34.8 grams of octane, I should produce 1.55 10 to the 3 kilojoules. So with that said, you are now ready to do your daily work. And when you're done with that, you can do another one so you can continue practice. And once you do that, we can call this objective done. So now you know how to calculate the amount of thermal energy using a chemical reaction, a balanced chemical equation. And with that, we close this chapter. So real quick review. We know that if we have a balanced chemical equation, you can get conversion factors from the coefficients, moles to moles. We can use those moles to moles to do conversions. to find out the amount of product you can make given the reactant, or the reactant you need given the products. And we can do that also with mass to mass, because you can change mass to moles, and then you can do what you were doing on number 2. And then we said, when we have 2 or more reactants, one of them will always be in short demand. So you can always find out which one is the limiting reactant. And once you know which one is the limiting reactant, the one that will produce the least amount, then that amount is what we call the theoretical yield. And if you happen to be given the final result from the lab, how much you actually made, then you can find the percent yield by doing a ratio between the actual product over the expected or theoretical product. And you can do all that beginning with moles or beginning with mass. And you just saw how we can also use that with energy. And with that, we are done. So when we come back next time, we will be going into week number 10, and we are going to go back deep into the atom to really study those electrons and see how those reactions are the real cause of all the reactions you see. So we're going to go into quantum theory when we come back. So see you later. Have a great week.